Okay, so I would like to talk about critical points and local extrema, and yeah, you all can point out that I don't know how to spell local. Whatever. Okay, so back to Calc 1.
You just literally took out.
Yeah, I took out the vowels. But sorry, wrong. I don't know why I took the vowels out of that word and none of the others.
Yeah, because that's how you roll.
Okay, Extrema you might think is extreme without the vowels.
Okay. Buy a vowel to fill in the topic today. All right, so back to Calc 1. What is a critical point in Calc 1?
Local minimum, local maximum.
Oh
my
god.
Okay, so I would like to think that a critical point happens,
Where the derivative is equal to 0.
yeah, where the derivative is 0.
Oh, you used the vowel.
Right? So what I'm thinking is derivative is 0, although I probably should add one thing. Or, yeah, or maybe undefined. Okay, so Railer keeps saying this thing, and it's driving me nuts. Okay, and I want to say that this is a good thought, but totally different. So, what was your thought? Say it loud.
The critical points where the slope changes from negative to positive.
Good. So, where the slope changes from negative to positive is a critical point. So the slope goes from negative to positive or vice versa, right? These things fit in there, but not all critical points have this property. Cool? These things, right, where the slope goes from positive to negative or negative to positive, right? Those are turning points. Those are really maybe more exactly like the maxes or mins, right? You guys see that? The critical points are just more the potential maxes and mins.
X cubed.
You guys see that? Yeah, think x cubed, right? Like, it doesn't actually go from, right, the slopes are always positive, right? But there's that spot where the derivative is 0. You guys see that? That behavior gets a lot more complicated in Calc 3 land, right? But it's still there, right? There's like some kind of saddle point might be the case. So when we think about critical points, I want you guys to think about potential, right? Not necessarily actual, but potential max, min, whatever kind of rando behavior can go on. Cool? So these are my potential local extrema. And in Calc 3 land, what am I going to change? So let me give you a precise Calc 3 definition. So a point, maybe let me say AB, right, is a critical point for the function f of x and y if, what does it mean for the derivative to be 0? What's the derivative?
The partial derivative of x and the partial derivative of y.
Yeah, it should be kind of the slope of the tangent line. That has something to do with the partials in x and y.
Rate of change at a point.
Yeah, which is really kind of like the rate of change at this point in all directions, right? You guys see that? So we could write several different characterizations. We could write if the tangent plane is horizontal. We could write if fx is 0 and fy is 0. Or we could write my favorite, which is if the gradient of f evaluated at AB is the 0 vector. You guys see that? We could also write if the directional derivative in any direction is 0.
Or undefined.
Good, and we still have to throw in the undefined thing, right? So if the gradient is 0, or if the gradient of f evaluated at AB is undefined. You guys see what I'm getting at here? Like with any of those calculations, we're getting at the tangent plane is horizontal or doesn't make any sense.
Would that be like a rotation of x cubed? If you rotate it like this way?
Yeah, so if we kind of thought about making a shape that was x cubed, rotated a little bit, and then like filled in on the sides.
Full 90-degree rotation.
Full 90-degree
So
rotation.
that wouldn't even be a function.
Oh,
Yeah, so that's
yeah,
what we need, it's
perfect.
undefined.
So cube root of x has an undefined slope, right? You guys recognize this? Maybe let's go back to Calc 1 land for a second. Here's an example where the derivative is undefined. So say f of x is x to the 2/3 power. What's f prime in the case of x? F of x is x to the 2/3 power. So what's f prime?
2/3 x
2/3 x to the
negative 1/3.
negative 1/3, right? Which is 2 over 3 cube root of x, right? You guys see that? When is this thing 0? Right? A fraction 0 and the top is 0, right? So when is 2 0? It isn't? Okay, so f prime of x is 0 has no solutions. When is f prime undefined?
When x is less than 0?
No. You got too ambitious there, Ben.
Oh,
Because it's a cube root, right?
okay.
The cube root knows how to deal with negative numbers.
Oh, okay.
When x is
What's the problem? Well, I'm dividing by something, right?
Oh, if when x is 0.
So I should worry about when x is 0, right? So f prime is undefined when x is 0. Anybody got a graphing calculator? You want to know what this thing looks like? No, it's not too bad.
Yeah.
So let me maybe do the dumbest thing I could do to approximate a graph for this.
How do I put a cube root?
Cube root of x looks like this, right? If you square a negative number, you guys see that this is cube root of x squared. So if you square a negative number, what are you going to get?
Positive.
Positive number, and the size is going to change, right? But it's positive. So since I haven't labeled my y-axis here, you see that? Like the size change is going to be funny. Like it's not uniform. So it's not just a relabeling. It's a little bit of a stretch and some kind of funny spots. But this is roughly going to look like this. And to get full credit in Meryl's class, I think we have to do this, right? Someday she's going to watch these and realize I make fun of her occasionally. Cool? Don't tell her to watch these. You guys do have much more precise habits, though, than the students that I teach Calc 1 and 2 do, which is good. So, what's the deal? What's going on there? At x is 0, what's happening? Yeah, there's a cusp there, right? Why is the derivative undefined? What the hell's up with the tangent line?
Is that a point?
The tangent line is vertical.
Yeah, that's actually the right answer. The tangent line there is vertical. You guys see if you come into it from this side, right? Remember, a tangent line is made out of the limits of these slopes of secant lines, right? So if you come into it this way, it's tipping up. If you come into it that way, it's tipping up, right? So your slope here, your tangent line, is just going to be infinite slope. You guys go with that? What's up? You graph the derivative.
Okay, this one.
Yeah, so if we look at the derivative, right, the graph of the derivative function looks something like this.
Okay.
Right, and the reason for that is that the slopes out here are, this is not actually quite right,
Okay.
but the slopes out here are pretty flat, right? And then they get really steep.
Okay.
And then they're really steep and they get flatter. Is that kind of with me on that? Okay, so this undefined business though, right? Why was I doing that? What is this thing? Like, so I calculated the derivative, I set it equal to 0, I solved, I didn't get anything. I checked the undefined spot, I got x is 0. What the hell does that mean? What was I searching for?
Critical point.
Yeah, I was looking for critical points. But why was I looking for critical points? Like, why do you do this?
To find the maximum.
Yeah, you're trying to find the maxes and mins, right? Does this function have a max or a min? Yeah, hell yeah, there's a minimum right there. You can see it plain as day on the picture.
Does it stop at the origin, or does it kind of go down to infinity?
No, it stops at the origin, right? If you plug in 0 here, you get 0. Easy peasy. So this thing does actually have a minimum value, but when I just set the derivative equal to 0, right, I didn't find it. The reason I didn't find it is that the derivative, right, went from negative to positive, right? It switched sign, but it did that by jumping. That's why I have to check this undefined thing, because sometimes it just does that by jumping. You guys cool with this? So we have to check, right, when is the slope horizontal, and also when doesn't the slope make any sense, because it may have jumped past without us noticing. You guys cool with that? If the derivative's continuous, right, do you need to check the undefined thing? No, right? Because continuous kind of means defined, right?
Yeah, I was about to say.
No jumps.
Yeah, so if it's continuous, there aren't any jumps, you don't have to check the undefined thing. You just need to check the undefined thing when there's problems with continuity, and those are a hell of a lot harder to spot here, right? You guys see that? So you're going to have to like set the bottom equal to 0 and solve, and that's going to be weirder here. Cool? Questions, Steele? Okay, so that's how you find a critical point, right? You just take the gradient, set it equal to 0, solve, or take the gradient and look for discontinuities. Now, I'll spell local for you, but I'm still going to spell Extrema with the. Still going to spell Extrema with an X. Okay. Did you say the thing I wanted to ask? What are Extrema?
We just said that was pretty extreme.
Oh, good. Glad you guys caught that one. Okay, so I need to define what a local max is.
Highest point of a function within a given area.
Yeah, it should be kind of the highest thing around, right? You guys with me on that?
Mm-hmm.
So we're going to say f of x and y has a local max at a, b if f of a, b is bigger than or equal to f of x and y for x and y close to a, b, and I'm kind of leaving off what close means. You guys see that? In other words, right, if you have some surface that looks like this, oops, it's not gonna work. You guys all got eyes on my funky surface here? Fact. It does not matter what the scale is on this picture. That's what I mean by close, okay? You guys see that? Now let's ask our questions about our, you guys remember we kept running into these things where there were these like troughs, right? Where everything was all kind of the same height. Does that count as a local max in this case?
No.
Yeah.
Oh,
Yeah.
drop.
Would be a range of points that would be your local max?
Oh.
Yeah, so I'd have like a whole bunch of points. So one of those could be something like, what if we did an example that was like g of x and y is, I think this was one of our ones we did before where we did like cosine of y squared plus x squared.
Oh, that's what I meant by drop.
Right, this is cosine of the radius, right?
Square.
Squared. So this thing is going to start out here at r is 0. We're going to get
1.
z is 1, right? And then as we go out, where's this thing going to hit 0?
Where x squared plus y squared equals pi over 2.
Okay. For the radius is the square root of pi over 2, right? So out here with, there's going to be some circle, right? It's going to be a radius thing. And that's going to be the height z is 0. And then out here a little further, we're going to get to
Z equals -1.
z is -1. And then out here a little further, we're going to get to,
Another 0.
yeah, so z is 0 again, right?
One more for z equals 1.
You guys see this? And I know that the biggest and smallest this thing can get
Is 1 and -1.
is 1 and -1, right? So this guy in the middle, right? That's a local
Max.
max. And then this whole level curve here, right? The z is -1 level curve is going to be a
Local minimum.
local min, as long as I define local min similarly.
Question.
Oh, greater than.
So it says if f of the function f of ab is greater than or equal to f of x y, but does that include it being a critical point? So
Yeah, so I haven't said that this is necessarily equivalent to being a critical point. Do you guys see that?
yeah.
Like right now I have this critical point idea that's over here, and over here I have this thing about, okay, local max means this thing.
But when it, like approaching the top of that peak, wouldn't that also be a max then, or how do you?
Okay, so if I think about pegging some other point, like say this one,
Yeah.
right? In some little neighborhood around there. Right, so if I think, okay, down here, right, is the thing that went to that. You guys with me? So this is a point, right, that's an x, comma, or let me just think that's an a, b, comma, f of a and b, right? So down here's my point a, b. So close to that thing means in some little disk around that guy. And what this says is that f of AB is the biggest thing in some little disk. But if I push that little disk up, right, I get this guy.
Yeah. Okay.
That's bigger. This thing couldn't be a maximum. You guys all see that?
So it's just the highest point in the neighborhood. It doesn't have to actually have like a slope of 0 or undefined.
Yeah, I haven't said that so far. That is true, but I haven't said it so far. You guys all see that? Like if the slope wasn't flat there or broken, then I could find a direction in which I could climb, right? In fact, I could take that gradient, right? If it wasn't 0, it would be some number. That means the directional derivative in that direction would be positive, and I could walk uphill. You guys see that? Or maybe it would be negative, in which case I can walk downhill, right? Those are going to be the two cases here. You guys cool with that? Okay. All right. Should we use our knowledge of critical points to try to check that thing, or do you want me to give you the definition for local min? You guys trust that you can define local min? Oh, what the hell?
I was gonna say.
I'm just going to add it in red here, right? So we're going to say a local min instead of a max, and what's the other thing that's going to change in here?
Less than or equal to.
Yeah. Cool. Okay, now let's see if we can find the critical points for our example. I think we can do that. And then we'll talk about how to classify them, because we still don't know how to actually classify them. You guys see that? Like, so far I've given you, this is what a critical point is. Here's what a local max and a local min are. I haven't bothered to define a saddle, because I think you guys probably have an intuition about a saddle.
Yeah, I figured out when I was looking at test results, or was it the practice tests answer sheet?
Oh, yeah. So, since you guys have the concept of a saddle, it would be nice if I could find a critical point, right? And then figure out which one of those things it is. But we don't have that tool yet. So let's do our little example. Let's take g of x as the cosine of x squared plus y squared. Oops,
So,
g of
G of
x
y.
and y, right? Because we're in Calc 3 land.
Why is that? Why is a constant?
Yeah, we don't want y to be a constant. Okay, so what should I do to look for critical points? If I want to say find critical points of this.
We need derivative and double derivative.
Okay, so you need the gradient of g, right? Maybe being careful, because I'm learning to be carefuler. Gradient of x and y is what? Okay, good. It should be a vector, right? It should be made of partial x, which is,
Let's see, the negative sine of x squared y squared 2x. Yeah. There we go.
so I think I get negative sine of x squared plus y squared. Where did the 2x come from?
The chain rule.
Derivative of the inside. And then you get comma,
Negative 2y sine of x squared plus y squared.
oops, negative 2y sine of x squared plus y squared. Guys cool with this? Then we should,
Do it again.
no.
Test for W.
So why am I not taking a second derivative? Yeah, so far all I'm trying to do is find critical points, right?
Yep.
Set each
Set each one equal.
So critical points are where the derivative is 0, right? So I took a derivative, I'm going to set it equal to 0. So we should take this thing and wonder, when is this thing 0?
That's 0.
You can do
Yeah, so I'm going to do this. I'm going to do minus 2x sine of x squared plus y squared is 0. And then simultaneously, right, I need minus 2y sine of x squared plus y squared to be equal to 0. You guys with me on these? Okay, so how do you solve such things?
So we have the obvious that when x equals 0 or when y equals 0.
Okay, so you got x is 0 on that one and y is 0 on that one. Are those coupled together in any way?
No.
No. What did you do?
You know that x and y, do they equal the same thing? X and y equal now?
The x and y, they're outside the parentheses, so if those are 0, like, the entire thing's going to be 0. If it's on the inside, though, we can't say for sure.
That's good. What is the like algebra step you're doing to get from here to there? No, it's not assumption. You just don't recognize it for some reason.
Just dividing.
Divide by -2 side.
Zero product rule?
You're using the zero product rule, guys. Right? You have two things multiplied together. They're set equal to 0. You set one of them equal to 0 because you're smart. And the other one,
Yeah, one of them must be.
the other one could be 0, right? This is like groups of things. Right? If you have a total of 0 things, and they're in groups and of things, right? Then either you didn't have any groups or you don't have any things in the groups. You guys see that? So either 2x is 0 or yeah, or that crap with the sign is 0.
Which in this case would be x squared plus y squared.
Which in this case would be x squared plus y squared is odd pi over 2. Right?
Wait, isn't this is sine, so shouldn't it be just pi? Versions of pi?
Hang on. How does sine work?
So it's at 0, then
Sine works like this, right?
yeah.
Oh, I said odd pi over 2. And what
That's
I
what
should have
those
said
say
was even pi over 2.
So in other words, multiples of pi.
Yeah, so the pi's and pi's. Cool. Okay, how about this other one? This is when y is 0 or when same deal, right? Or n pi's. Let's go with n pi's. That's not really what I mean, right? I mean x squared plus y squared is n pi's. So maybe let me just say this guy. Or when sine of this graph is 0, right? And that's when the radius is of pi, right? Cool? Yes? Okay. I still don't know how to classify these, but my picture of sine is probably going to give me some intuition, right? Is that? I could maybe help. My picture, maybe a picture of cosine would give me better intuition. You guys cool with that? Like I change this to polar and then think that way. Alternatively, I really, really need a classification test. So, how do you get a classification test?
Now we did what we should get.
This is that one we use the second derivative, isn't it?
Should graph this one out? Yeah, we definitely should graph this one out. You should, by the way, if given the opportunity, graph this silly thing instead of using this determinant test. Okay, it is a little bit easier usually to get some kind of intuition in the problem. This other thing is just a black box. You just calculate the number and then you look up what it means. Cool? I'm going to stop this and give us the test.